Okay, hi everybody, this is video 2 in our series looking at advanced higher physics papers, and in this one we're going to look at angular motion. So I'm going to the Calder Glen High School physics website and we're going to look for an angular motion question. So if I click on past papers, there's a whole list of past papers there thanks to Mr. Mackenzie, but let me draw your eye to another resource here. It's Advanced Higher Physics Past Papers by Key Area, and thanks to Mr. Davey for this resource. If you click on that, then you'll get to an interactive PDF, and if I scroll down you can see all the key areas in the Advanced Higher Physics course, and there are the questions that are in the individual papers from 2016 to 2022. So if we're looking for an angular motion question, it's usually question 2, and if you click on one of them it will take you straight to the question, and tagged on the end of it is also the SQA marking instructions as well. It's a fabulous resource, so a big shout out to Mr. Davey for that. Now the eagle-eyed amongst you may notice that Mr. Davey has a 2020 paper there. Now there were no exams in 2020, but the paper that had been written for that year was released the following year in 2021, and schools were able to use it to generate grades for their candidates that year. So it's now called the 2021 Assessment Resource. It's available on the SQA website, and it's also available on the Calder Glen High School website. So that's the first one we're going to have a look at today, and we're going to have a look at question 2, and it's on angular motion. So a cyclist is using an exercise bicycle, and a large flywheel forms part of the exercise bicycle as shown in the figure there. And the rotational motion of the flywheel is monitored by sensors at its outer edge. Data from the sensors is used to calculate equivalent linear speeds, which are displayed on the screen, and the cyclist is pedalling steadily, and a constant linear speed of 6.7 meters per second is displayed on the screen. The flywheel has a radius of 0.35 meters, and we have to calculate the angular velocity of the flywheel. As soon as you see that word calculate, you go straight to your relationship sheet, and if you're looking for a relationship sheet, then you'll find one on our school website. It's under useful documents, and you should have a relationship sheet with you at all times. So the relationship we're looking for in this case links linear speed with angular velocity. There it's there, v equals r omega. So let's jot that down, v equals r omega. It's omega we're looking for, that's the angular velocity. So omega equals v over r, and sub in the 6.7 meters per second, and the radius was 0.35. And if you do that on your calculator, you'll get an answer of 19 radians per second. And if we check that with the SQA answers, we can see we've got that right to 2 sig figs, and on the right hand side there you can see the usual accepted answer up to 4 sig figs there. But make sure your answers go to the same number of significant figures that there are in the question. 2A part 2, the cyclist now stops pedalling for 5.5 seconds and the flywheel slows down due to a constant frictional torque, and it's got a constant angular acceleration of minus 2.4 radians per second squared. Determine the number of revolutions made by the flywheel in this time. So let's list our 5 quantities that are in the angular equations of motion. So we've got angular displacement, initial angular velocity, final angular velocity, angular acceleration, and the time. The time is equal to 5.5 seconds. We also know the angular acceleration is minus 2.4 radians per second squared. We're looking for the number of revolutions, so we need to find the angular displacement first. That's theta, that's what we're after. And we need one final thing, which is the initial angular velocity, which we got from the previous bit of the question. That's 19 radians per second. Now we're ready to go. We need the equation of motion that doesn't have omega in it. So it's the rotational equivalent of s equals ut plus a half at squared. And there it is, theta equals omega naught t plus a half alpha t squared. And we're just going to sub everything in there. So it's 19 times 5.5. And because it's a negative acceleration, instead of a plus sign there, I'm going to put minus a half times 2.4 times the 5.5 squared. And if you do all that on your calculator, you'll get an answer for the angular displacement of 68.2 radians. And I'm not rounding that because that's not my final answer. We want the number of revolutions. Now there's 2 pi radians in a revolution. So if we want the number of revolutions, we just divide 68.2 by 2 pi, and that gives us an answer of 11 revolutions. Although when you do that on your calculator will say 10.854, and you might be tempted to say, well, that's only 10 complete revolutions, but the question doesn't say how many complete revolutions are made by the flywheel. So if it's 10.8 and we're rounding to 2 significant figures, then it rounds up to 11 revolutions. In part 3, the cyclist reduces the frictional torque acting on the flywheel. Now, torque doesn't appear until the next key area, which is rotational dynamics, but it's crept into this question. So the frictional torque is reduced, the cyclist resumes pedalling until the screen again displays a linear speed of 6.7 meters per second, and the cyclist then stops pedalling for another 5.5 seconds. And we have to state how the number of revolutions made by the flywheel in this 5.5 seconds compares with your answer to A part 2, and we have to justify our answer. Well, if the frictional torque is smaller, then the angular deceleration will be smaller. And we can see that from this relationship where tau is the torque, I is the moment of inertia, and A is the angular acceleration. So if the angular acceleration is smaller, then the wheel will spin faster for longer, so the number of revolutions will be greater. That's pretty tricky. Let's have a look at the marking instructions. They simply say that for one mark there's a greater number of revolutions, and for the second mark because there's a smaller angular acceleration. And then 2 part B, the frictional torque is produced by a brake pad that's in contact with a flywheel, and that brake pad can be at 4 possible locations, and we have to state which of these positions would allow the brake pad to produce the greatest frictional torque on the flywheel, and justify your answer. Now, it would be position D, and if we think about this relationship on your relationship sheet, tau equals Fr, where tau is the torque, F is the applied force, and R is the distance from the axis of rotation. So for the same applied force, the torque will be greater at a bigger distance from the axis of rotation. Well, let's have a look at the marking instructions for part B. Then it's position D for 1 mark, and then the justification is that you're applying the force at a greater distance from the axis of rotation. And if it's underlined in the marking instructions, that's the statement that must be in your answer. Okay, let's have a look at another angular motion question, and this time it's the 2022 paper. A very different question. Again, we've still got motion. This time it's in a horizontal circle. It's about a merry-go-round at a fun fair, and the merry-go-round is accelerating uniformly from rest, and it takes 18 seconds to reach an angular velocity of 0.52 radians per second, and we have to calculate the angular acceleration. So let's make a list of our 5 variables, and we will fill in what we know then from the question. So we're told that the time it takes is 18 seconds. It starts from rest, so omega naught is 0, and it reaches a final angular velocity of 0.52 radians per second. And we have to work out the angular acceleration of the merry-go-round. And we don't know what the angular displacement is. So we're looking for a rotational equation of motion that's got those 4 variables in it. So the one we're looking for is omega equals omega naught plus alpha t. and make sure your alpha looks like an alpha and not an A. Let's sub in the numbers. Omega is 0.52, and that's going to be equal to 0 plus alpha times 18, and it's the alpha that we're looking for. So if we rearrange that, then alpha is equal to 0.52 divided by 18, and if you do that on your calculator, you'll get 0.029 radians per second squared. And then checking the SQA marking instructions, that all looks good to 2 sig figs. Part 2 then, calculate the angular displacement of the merry-go-round in this time. So we're looking for one of the angular equations of motion that's got theta in it. So let's use this one, and we'll sub in everything we know. The final angular velocity is 0.52, the initial angular velocity is 0, and the angular acceleration is 0.029. And then we're going to rearrange this and find theta. So 0.52 squared divided by 2 times 0.029 will be equal to theta, and if you do that on your calculator, you'll get an answer of 4.7 radians. And let's check that with the SQA marking instructions. Now on the left hand side there, they've got the same answer, but they're using a different equation of motion, and if you look on the right hand side, there's the version we've used. And again, watch your sig figs. 2 sig figs in the question, 2 sig figs in your answer. Moving on then to part B. 2 students, X and Y, are riding on a merry-go-round, and the students are sitting on horses as shown in figure 2A, and we have to explain why student Y has got a greater tangential velocity than student X. Well, student Y is at a greater distance from the axis of rotation than student X is. And if we look at this relationship from your relationship sheet, then for the same angular velocity, then student Y will have a greater tangential velocity. And let's have a look at the SQA expected response. So it's B part 1, so 1 mark for stating the relationship V equals R omega, and the second mark for stating it's because you're at a greater radius but you've got the same angular velocity. And on the right hand side, you'll see you could also have answered this question using speed equals distance over time, and student Y will travel a larger circumference, that's a bigger distance, in the same time. Okay, final piece of the question, state whether the centripetal acceleration of student Y is greater than, equal to, or less than the centripetal acceleration of student X. Well, we've got a relationship for this as well on our relationship sheet. The radial acceleration equation. In fact, there's 2 versions of it. A equals V squared over R, or A equals R omega squared. You'll find it on your relationship sheet, although it's all written in one line, so we want to pick the R omega squared version, because if R is greater but the angular velocity is the same for them both, then the centripetal acceleration will be greater for student Y. How do we write that in words then? So for the same angular velocity, R is greater for student Y, so student Y's centripetal acceleration will be greater. There's the SQA expected response for part 2. 1 mark for saying the centripetal acceleration is greater, and the second mark for saying that student Y is at a greater distance from the axis of rotation. But you must relate it to one of those equations and make the statement that the angular velocity is the same for both students. So there's a huge variety of angular motion questions. It might be a horizontal circle, might be a vertical circle, might involve radial acceleration or centripetal force. So I think in our next video we will have a look at some specific examples of centripetal force questions. See you in the next one.